So shall I start? Oh, I see. So I see.
Yes,
Recording
yes.
is on.
Sorry, I'm late. Sorry.
That's okay. Just a sec. Here we go. So today's lecture is dedicated to the constant normal forms, nilpotent integral separators, and Thompson theorem. Well, important thing what you need to understand about this lecture that we will do some proof today. Like we'll be proving some facts, and those facts they are not very complicated in general. They may seem quite the opposite, rather simple. But to prove them, you need a precision, right? So today's lecture is about precision. We will be writing very precise things, and we'll be discuss very specific in very specific details. Okay, because we work with a tensor object that you just can't just say whatever you like. So we start with the several facts we need, as usual. Okay, as you may recall from our earlier lectures, we have a Frobenius Ii theorem. Frobenius Ii theorem states that if you have a pairwise commuting vector fields, which are linearly independent, then you can take them as a coordinate vector fields. It means that you can choose a coordinate system for which these vector fields will be the coordinate vector fields. But this choice of the proof of the theorem and the choice of this coordinate system is usually done using the one-parametric groups of diffeomorphisms. And in our case, we need to look into the coordinates. What is the meaning of the coordinates? Okay, so it is simple. What is the coordinate system? The coordinate system is a collection of functions. Okay, so we have a collection of vector fields, and thus we have a collection of functions. What are the relations between them? Well, we want this collection of functions to be, first of all, functionally independent. In general, it means that the differentials are independent at least in one point, usually at in the origin. We always work in the neighborhood of a given point P, as in previous lecture. But in our case, we already have a condition that the vector fields are linearly independent. So we want to put the following restrictions on the functions. So we have k vector fields, and the dimension is k plus m in our case. So we put a restriction like this. See, we say that if we take a lead derivative of function f along psi I, fj along psi I, it is either 0 or 1. 1 it is if those indices coincide. So that is a very important formula, and we see that the rest of the functions, g functions, they are the common integral. That means that they're constant along all of the integral trajectories of the xi's. So when we're choosing these functions, that's what we will do in our proof, precisely. We will choose sometimes functions f. Important things to know is that functions f, they're differentials. They are pairwise independent, okay? Because of this condition, because xi are independent, so it's simply if you take linear combination of these functions and take differential and you differentiate them along the psi, and then you look look at the linear combination at given point, and you will see that each coefficient must be 0. So it's a simple linear algebra. But what you need to know is that given these functions, they are already functionally independent. Moreover, they're independent of the functions g. G are different. They are the integrals, right? So they are not their differentials and the differentials of functions f. They do not intersect. The linear spaces they span in cotangent bundle, they do not intersect. So basically, when you have functions f, you need functions g with only one condition. Those functions g should be linearly independent. This will in turn guarantee that the entire collection of the functions f and g are all functionally independent, and you have coordinate system. So the algorithm is like this. You start with the f, you find f for those xi's, then you find linearly independent integrals, and then you combine them together. They are already linearly independent. You have a coordinate system. So this is the trick we will use. Okay. The second thing is how we will use it. Okay, for example, what we said that you need to choose G, right, integrals, but sometimes in our case, we will already have some integrals and we need, and then we ask the question, if we have, let's say L integrals, L, this is L, it's smaller than M, right? Then I ask oneself, like, can I find more integrals? Like this choice, do this choice of L integrals already, like, can you come up with the L integrals that you cannot add enough integrals for this distribution, right? It's not the case, right? So you can always add enough integrals. The proof is rather straightforward. We apply Frobenius theorem, right? We get the coordinate system. Then we write the following sort of Jacobian matrix for the system of the functions G1, GL. This matrix, it has L rows and M columns. So it's like long matrix, right? So, and we see that the rank of this matrix is K. So without loss of generality, we may assume that the first K by K matrix, its determinant is not zero. This implies that we can take these functions and we can add those Y functions, see, to this G. And we get the complete collection of integrals. Because if you have the minor K times K, the first one, it means that the differentials of them these collection of differentials is independent. Okay, so we can always add the existing collection of integrals up to the complete collection of integrals. So that's what we will do. Okay, now we're ready to proceed. This was some insight concerning the coordinates. Okay, so we start with the linear algebra. Imagine we have a vector space, like the simplest thing, and we have subspace, right? And we have a linear operator which respects the subspace. It means that if you apply L to W, it will send W into the W. So we have two natural operators. One is called restriction, right? Because W is an invariant space, then we can take a vector from W, and LW will be in the same space. So it's a simple restriction. The other thing is a quotient operator, which is kind of more complicated, because what you do here is you take a quotient space, right? The elements of the quotient space, they're those equivalence classes, right? So you take some vector and you add all the vectors from the W. And if you apply L, you will see like action of this quotient operator. It goes like this. You apply it to this psi, and it is the same as applying L, and you see, because this eta is from W, it is L eta is also from W. So we see that the result of this operation, it does not depend upon the choice of the eta. So it is defined on the equivalence classes. So it is in fact an operator which acts on a quotient space, right? In coordinates, what does it mean? If we pick bases, like basis vector fields, A and M, as usual, numbers are the same as in previous, we'll see that the matrix looks like this, right? So this eta 1, eta k is a basis in W. This implies that if you apply a vector from W, it will stay in W. And L2 is a quotient operator. We see that if we apply a vector field from which has like this addition in W, and we apply it here, we'll see that this addition changes the way, the controlled way, right? So it will be some L1 plus M something, but still L2, like it acts on the part of the vector which is expressed in terms of psi, right? So it acts on a space which has basis psi, and we see that basically psi is a basis in quotient space. So it's a rather simple construction. The only purpose of this slide was to show you where in matrix of L those restriction and quotient live, right? In the left up corner you have a restriction, and then the right lower corner you have a quotient operator. So we are ready to ask ourselves, because we do differential geometry, we're ready to ask ourselves, well, how do we apply this construction, right? What is the analog of this construction for the distributions? So we deal with primarily in this part, we deal with the integrable distribution. As you may recall, a distribution is a collection of subspace. It means that in each point of the manifold, you pick a subspace of tangent space. Then those subspaces, they should be locally generated by a collection of vector fields. This implies that the distribution is smooth. And this is the Frobenius theorem says when gives us the necessary and sufficient condition for this distribution to be integrable, that is to exist the foliation. Foliation are leaves which are tangent to these subspaces D. Okay. So among all the subspaces, we pick the distribution. We are interested in distribution, which is L invariant. What does it mean? It's trivial. You just pick a vector field which lies in the distribution, and then you apply operator L, and it still lies in the distribution. It means that arbitrary vector field. So it means that L acts on this distribution. So same as before, right? We can make a restriction, right? We get an operator, we restrict it onto this distribution. If this distribution is integrable, it means that we have restricted an operator onto the leaf. We already have a operator field not on the entire neighborhood, but on the leaf of smaller dimension. It's important, which goes through a given point, right? And we have this leaf, and it is equipped with a operator field, and like it's very simple to show that if operator L is Nijenhuis, and then the restriction is also Nijenhuis. So it's a simple fact. But here we're interested in quotient operator. Quotient operator is a little bit more complicated stuff. So to understand the problems we're dealing with, what we need to do is pick coordinates. We will use this many times. Adopted coordinate system. Adopted coordinate system, it means that we pick the coordinates such that our distribution, the one we call D, right, is spanned, right, by the first coordinate vector fields. X1, xk are the first coordinates, right? So partial x1, partial xk will span the first the distribution. In these coordinates, because we already know this from linear algebra, right? We get that the L is in the following form. The L1 is a restriction. Restriction of the operator, it implies that you fix the leaf. To fix the leaf, you fix the coordinates y coordinates. They are coordinates on the quotient space, on the space of leaves, and x's are the coordinates on the leaf. So it's we see that this is simple, but L2 is quotient operators. It's supposed to be a quotient operator. As I said, y's, they're the coordinates on the quotient space. So for this operator to exist on quotient space, right, it should not depend on x. Why? Because, well, if you imagine this operator and you try to define the operator in point y and it depends on x, you just can't pick the right operator, right? You need something more complicated. If you want to do like simple quotient factorization, then you need it must be simply defined, right? There should be no dependence on x here for this L2 to define quotient operator. So we see that we have a differentially geometric condition, right? In linear algebra, we did not have any conditions of this sort. because quotient operator, it was defined always. Here, to define the quotient operator, you need a differential geometric condition, so it should not depend on x. Okay, this is the setup. Now, as I said before, you can look at this operator, and if you just go straight ahead and write Ninja Distortion, you will see that in applying x1, xk, because they do change, and y1 and ym, they're supposed to be constant after restrictions. So you'll see that you just get like simple formula for the Ninja operator for L1. So the question is, what happens with the L2? If we have a quotient operator, do we have a Nijenhuis operator, right? Of course we do, but to do that, before proving that, we need some more invariant definition of what we said. We said like the L2 should not depend on x, but we have chosen the adopted coordinate system, and it is okay, but we can change coordinate system, right? And we need to ask ourselves what coordinate changes are allowed, which are not. And this is kind of complicated to formulate. So we will need a more invariant formulation. It goes like this. Take any vector field, given vector field psi, it is said to be d-preserving. It means that it preserves the distribution. If it preserves distribution in the following sense, you take any vector field in D, and then you commute, eta is in D, and you commute, like in usual vector field commutation, psi and eta, and it still lies in D. So it's just like rather simple. So like if you have two d-preserving vector fields, then you can easily see that they're commutator because of the Jacobi condition. It's still a d-preserving vector field, right? So if we have distributions, then all the vector fields that preserve this distribution, they form a subalgebra. These vector fields, they are closed under the commutation. This is important remark, but not for our science. For our mathematics, we do here. So, but if now we go back and write this vector field, write this condition in terms of coordinates, we'll see, okay, let's write psi in coordinates. We see that we have first k components of vector field, like we decompose it into partial psi, partial x, y, and stuff. And then we take the rest, which are the components. I used bar for the notion, are components in decomposition in partial y. I used the same notation in previous lecture, so if you have seen this lecture, there is no surprise here. Bar does not mean any conjugation, it's just a notation. So if now I ask myself, in given coordinates, what does this condition look like? It looks very simple. If you commute, because this is adopted coordinate system, and D is spanned by first by partial xi's, right, by those vector fields. So we need to commute, and if you commute, we'll see that for this vector field to lie in a distribution, these components, they should not depend on x, right? Because, well, if you commute because you have a basis vector field, then it's just simply in local coordinates you get the just vector field with coordinates being partial derivatives, and for the result to lie in this subspace, this should be 0. Okay, it's rather simple. But so it's a simple observation, but it is important. So if we take psi in this following form, and it is d-preserving, right? It preserves the distribution. We see that for this operator not to depend on x, we can say that the following must hold. This is the proposition we actually proved by simple observations. We have shown that if we have vector field, any like arbitrary, and we apply L to this d-preserving vector field, then we get a D-preserving vector field. Look, so if it does not depend on y, and we apply the vector field with
I'm sorry, I don't hear anything. So your mic must be something. You lost your mic? I don't hear anything.
Yes, Andrey, there is no sound. Please check.
hello, I'm sorry, something happened, and I was kicked out of the meeting.
Fine. Now it's fine.
Okay. So back to our presentation. Okay. Well, do you see my presentation?
No.
No. Okay.
Oh, I see.
Do you see presentation now?
Yes.
Yes. Okay. Let me try again. Okay. Do you see presentation now? Is everything fine?
Yes.
Okay. Finally, let's go back. We are losing a lot of time with this technical difficulty. Okay. Too much time. So we have proved the following very simple conditions. So we have shown that if for the operator to be to have a good quotient, we need for every D-preserving vector field, the L to this operator, L to this vector field should be D-preserving. Okay, we have shown this. Now we move to the next. Now we will prove that this operator, in fact, is a Nijenhuis operator. That everything we did for a reason, right? It would have been really disappointing if it wasn't, right? So we just spent 20 minutes discussing quotient operator for no reason. Okay, so what we do, we'll take an Nijenhuis operator L and then L invariant integrable distribution, and if the quotient operator exists, we assume that it exists because this is the different type of differential conditions which do not which basically have nothing to do with a Nijenhuis operator, right? They exist on their own. So, and then we just do straight ahead calculations. See, we substitute this. We get the following formulas. The M is an operator in this form, right? You have L1, L2. We're interested in the second part of the matrix, those columns. See, so this is what we get. after applying operator, and we see this part vanishes because those are coordinate vector fields, and these three brackets, they survive. And then we see the following, that the formula becomes like this. We have a part, because what is the result of the Nijenhuis Nijenhuis torsion? It's a tensor field. You like plug in two vectors and you get a vector. So if you want something to vanish, it is a vector vanishing, right? And vector has different coordinates. In our case, we see that we have a formula which we do not need to calculate in its entirely. So we see that we have a part which are the coordinates in y, and we have a dots which stand for the coordinates in x. We see that if we want to fully computate the Nijenhuis torsion, we need to open those brackets and carefully calculate and gather all the terms together. We'll see that here it will be huge formulas, but it doesn't matter that they do exist, because those coefficients, they are in front of the partial xi's, so they vanish on their own. And this part, this is a summation actually. Here's the gamma, summation is gamma, is from 1 to m, like on the entire y. So we see that these parts are vanished because we do have our, we have those basis vector fields. So if they do vanish, we get the following formula, and this is exactly the formula for the vanishing of the Nijenhuis torsion for the L2, right? We see that this should vanish because, again, the vector vanishing, and we have that we indeed have proved that the corresponding operator field is a Nijenhuis operator. Here, when opening these brackets, we did use, you can see that we assume already that L2 depends only on y's, right? So for the derivative on x being 0 of this part. So it's important. It does not hold for any operator in this form. It does not happen. But for the correctly defined quotient operator, it holds. So such an amazing result. So now we have what we did from the start. Let us review some. We first discussed integrals, how we do construct precisely the coordinate system when I have a k-commuting linearly independent vector fields. And we discussed a question about quotient operators. Those are technical results we need to attack, like the main theorem of today, like the Thompson theorem. Why is it important? Why the Thompson theorem is important? It deals first for us. It deals with the normal forms, right? What are normal forms? We have already discussed in last lecture, like the previous, not last previous. In previous lecture, we have discussed the following normal forms. We have discussed diagonal normal forms for real eigenvalues, and we showed that if operator is diagonalized in each point and Nijenhuis torsion vanishes, that it can be brought to diagonal form. This is the direct corollary of the splitting theorem. And we also found out that in general, the diagonalization problem relates to the so-called Heintius torsion, which is defined using Nijenhuis torsion. So Nijenhuis torsion plays an important role in answering the question about diagonalization. We also found a normal form for the diagonal operator. We saw that the coordinate change, how they do affect this operator and stuff. But the simplest form, if you ask anyone, like the simplest form of an operator is, of course, operator field is a constant form. This is like the first that comes to mind. When you deal with the tensors and you want to make them constant, it's not a simple thing to do, because if you if you recall like how you do it in the Riemannian geometry, you will see that the question of existing of coordinate system for the metric to be constant, it is equivalent to the vanishing of the curvature tensor of the corresponding Levi-Civita connection. Thus, to answer this question is when you have such a normal form, because no one expects every metric to be of constant form. It requires some work, some theory. Here's basically we will need the similar things, right? So we ask a question: when operator field, which is not Ninjahuis, just let's come up with any operator field with real eigenvalues. All the complex eigenvalues, we will discuss them in the following lectures, right? For now, we just deal with the real eigenvalues. It's still rather complicated. If you just add the complex eigenvalues into the mix, it will become too complicated for my taste. So we deal with only real eigenvalues in this lecture. So when can it be brought to constant form? The thing is, if you remember the definition of the Ninja operator, but we can go back and look at the definition of the Ninja operator for quotient operator, we'll see that you have a derivatives here. So if L2 is a constant operator, it is Ninja, right? If this formula was to help you remember the original formula for the Ninja distortion. So we see that the Ninja distortion for a constant operator vanishes. It means that this the vanishing of the Ninja distortion is the vanishing of the Ninja distortion is a necessary condition, right? So this is the necessary condition. The other necessary condition, of course, is that the eigenvalues of the operator are constant functions. It means they do not change from point to point. The same thing is the coefficients of the characteristic polynomial are constant functions. They do not change from point to point. And the other necessary condition, of course, is that Jordan blocks, the structure of Jordan blocks, it does not change. You have a no transformation, which is, of course, rather obvious, because you see, but it's not useless. This necessary condition is not useless because you can take eigenvalues to be 0, right? You have Ninja distortion to be 0, but still you have some like transformation bifurcations. So in general, you need to add this conditional. So those are necessary conditions. Okay. Applying splitting theorem to the operator which satisfies condition 1, 2, and 3, we get the following. We get that our operator is split into the operators with single eigenvalue. As eigenvalue is constant, then L minus lambda identity is also an Ninja operator. In general, it's not if lambda is not constant, but in our case, it is an Ninja operator. So what we did, using splitting theorem, we immediately reduced the question of existing of constant normal form of any operator field to the following question: when nilpotent Ninja operator can be brought to constant form, nilpotent. This is the question we are going to discuss. This is like the main result. It deals with the Thompson theorem. It actually answers this question. To attack the Thompson theorem, we first need some facts from linear algebra, because, well, it all starts with the linear algebra. You should always keep in mind that when analyzing Nijenhuis operator and Nijenhuis geometry, basically you have a lot of local Nijenhuis geometries, way more geometries than you have, for example, in Riemannian geometry or pseudo-Riemannian geometry, because you have very many different cases, because there are a lot of cases of operators and they can look different and stuff and so on and so on. So the analysis starts with a single operator from the linear algebra. What is a nilpotent operator? Nilpotent operator is some operator. If you take it into some power, it is 0, right? The smallest power it is 0 in is called the height of the nilpotent operator, right? S. So it means that L in power S minus 1 is not 0, but in S it is already 0. So you have two natural flag of subspaces. Flags are like if you have subspace which is embedded into other subspace, which in turn embedded into other subspace, like growing subspaces, basically. So we see that this is one flag. This is a flag of images, right? Because operator is nilpotent. With each multiplication, the dimension of images of the image grows smaller and smaller and smaller until for the 0 it is just 0, right? It has dimension 0, it's just point. And for not point, just for just 0. And the kernel of L, it's the opposite situation. It grows bigger and bigger because L sends some vectors into the 0, then L squared sends more vectors into the 0, and so on, till the 0th operator has kernel which coincides with the tangent space. It means that it sends all the vectors into the 0, right? This is just growing. Those two flags, each of them, it carries enough information for us to reconstruct the Jordan normal form. For example, imagine that we deal with a kernel, right? And if we look at the Jordan normal form of the operator and we take the powers of it, we'll see that before the vanishing, we'll have almost all zeros, right? The only non-zeros will be the vectors which are about to become 0. They are exactly the kernels of the Jordan blocks of the dimension S, because we've already got up of the dimension S minus 1, because we've already got to the power S minus 1. We killed off all the Jordan blocks. Those are the pieces that left. So if you look at the dimension of the image, right, of the image of the last power before vanishing of the operator, you see that the dimension of the image is exactly the number of kernels, and the number of kernels is exactly the number of Jordan blocks of this dimension. So you see that like those flags, they do have enough information about the linear structure of the Nijenhuis of the linear operator. It does not necessarily yet to be Nijenhuis. Now, what about the corresponding distribution? Let's go back to the differential geometry. Well, we do know from the previous lectures that the images of the powers, they are integrable. So you have like the integrable flag. You have distribution embedded integrable, and you have a bigger distribution, and you have a more bigger distribution. It grows till you get to the tangent space, and you have such flag of distributions, which is good. But the problem is here is that the kernels in general are not integrable. So again, this flag is integrable for the Nijenhuis operator, and this flag not necessarily integrable. Here we give an example which was due to Kobayashi. In 60s, I think the paper was written. It deals with so-called zero deformable G structures. We'll mention them. That is how all these questions, because they were like Nijenhuis geometry deals with the Nijenhuis operator, but Nijenhuis operators, they appear in different branches of mathematics before we started doing this geometry. And that is why some of the questions and some of the results, they do in fact come from different branches of differential geometry. So we see that this example is in R4, where later we'll see why. You have to start with the dimension 4. It's not a coincidence. So you take those vector fields, like they're simple. You see those 3 are basis vector fields, and the last one is not a basis vector field, but the vector field which is changed by the 3rd coordinate. And we define the operator like this. It sends first to the 2nd, and it sends all these vector fields into the 0. And the matrix of this operator, like, it looks like this. You just calculate it straight ahead. You can just check that it sends 1 to 2, it sends 2 to 0, 3 to 0, and if you multiply it by this, you get 1 plus x3, and here you have minus 1 minus x3, so we get 0. So this is exactly the operator. Now, important thing is that those vectors, they span the tangent space. So what we need to do to ensure that the operator is Nijenhuis, we need just a collection of vectors that span a tangent space. We usually take the coordinate vector fields, but the fact is, because we deal with the tensors, any vector fields which span the tangent space will do. And those vector fields look nice. They're linearly independent, of course, right? They do not pairwise commute, obviously, because this vector field does not commute with this vector field, so they are not basis vector fields, but that's okay, doesn't matter. We see that the image of the operator image is is the span of partial x2. See, you have only what's one-dimensional. So if because of that, we'll see that those brackets vanish, because if we apply this is the image, it will be partial dx2, and here we do have some different we go through different operators, and we'll see that they do always commute with this one, right? And applying this, we also get 0, and we'll see that this operator squared is 0. So if we'll take all these three things and substitute them into the formula for the Nijenhuis torsion, then we'll get 0, obviously, right? Just all the summons, they're 0. And as Nijenhuis torsion vanishes, then this operator is a Nijenhuis operator. And if we look at the kernel, right, because the image has dimension 1 and the kernel has dimension 3, it is spanned by xi2, xi3, xi4. And we see that this kernel is not closed under the commutator, because the commutator of the third and fourth, this is exactly third and fourth, is xi1. So it's like bigger. So this is a good example. It shows that the image that the nilpotent case is more complicated, but we are now ready, right, to get to the Thompson's theorem, because if we recall, the question we have been asking ourselves is about constant normal forms. Then we see that the constant normal form does not necessarily in constant normal form, all the kernels, they are also integrable, because the operator is in constant form. So we know that the integrability of kernels, it does not follow from the Nijenhuis vanishing of the Nijenhuis torsion, but in our case, it is still a necessary condition. So we can add it to the list of necessary conditions, the fourth one, right? So it's Nijenhuis torsion, eigenvalues are constant, etc., etc. And if we look at the condition 2 and 3, we replace them for nilpotent operator, right? So we have a Nijenhuis torsion vanishes, we have nilpotent operator, and we add the fourth condition. We say that, well, okay, let's for our kernels, let them be integrable. And it turns out that this condition is already not only necessary but sufficient. This is the exact idea of Thompson's theorem. So Nijenhuis nilpotent operator can be brought to constant form if and only if all the distributions kernel k for different k's are integrable. That is the theorem. It's really nice. Again, as I said before, all this stuff, all this mathematics come from different branches. So original work was written in languages so-called G structures. Those are sub-bundles of the frame tangent bundle. It's a bundle of coordinate biases in tangent space. It's an interesting bundle. It's a very useful tool in the theory of bundles, and in our case, the group, the structure group of the bundle is just the group that preserves the Jordan normal form of our operator. It's called basically its centralizer, and this is and if all the eigenvalues or the Jordan form of the operator does not change from point to point, then these G structures are usually called zero deformable. This is exactly the language you can find in the literature, like older literature, but still some people do use it. So let's proceed to the proof. The proof actually heavily uses the things we have discussed in the beginning. Like we have discussed how we choose a coordinate system and why. And we start with the simplest case. Our proof, it will be by induction. The parameter of the induction is the height of the operator. Let's say we have a height, I'm sorry, this is a typo, it should be 2. It means that L2 is equals to 0, right? And L is not 0. We do not start with a 0 operator. We start with an operator which in being squared is 0. So what distributions in this case we have? We have two distributions. We have image and kernel. As it was mentioned before, in case of constant operator, the kernels are obviously integrable, so we need to prove only in one direction, like the necessity of these conditions is quite obvious. So we need to prove that sufficiency. So we assume that the kernel is integrable, right? So we pick an adopted coordinate system, which is in good terms with the distribution we have. Basically, again, the first k basis vector fields, they span the kernel distribution. In our case, we've already went over that several times. In our cases, operator being squared is 0. We see that the restriction is 0, and obviously the restriction of the operator on the kernel is 0. And we have that the factor operator is also 0. But here we have 0. It's a 0 matrix k times k. This matrix is m times m. And this matrix, this is the crucial part. Actually, it is from linear algebra, but it is important. You see, the size of this matrix is k times m, but k is larger than m. It equals or larger, right? So this matrix is either square matrix, right? K equals m, or it's a long matrix. It's a high matrix, like it has long columns and short rows, right? And this is important because later this is a crucial part. We see the difference between the kernel and the kernel distribution and the image distribution in this. So if we do have something like this, then we can define we can calculate the vanishing of the Ninja distortion. This m, it depends on x and it depends on y, on both coordinates. So if we take partial y's, right? We apply this. We apply it to this operator. We will see that the following Ninja distortion vanishes, right? And we will see that because all other terms of all our terms, they are 0. This is we have only one term left. Why? Well, because there was a basis vector field, then the term with L squared and L squared is also 0, so it vanishes for two reasons simultaneously. So now if we have those mixed L and X, we see that if we take the vector field of this form and commute it with any other basis vector field, we get a vector field from the kernel. See, we see that this commutation is vector field from the kernel. That is why when we apply L to it, right, we get 0. So the vanishing of the Ninja distortion in this case, it is equivalent to the vanishing of this commutator, of single commutator. We denote those vector fields like this, psi I, right? So those are the basically psi's are the columns of this matrix M, right? And we see because the rank of this matrix is k, it does not change from point to point. We see that this because of those conditions, we see that these vector fields, they are linearly independent because there are m of them, right? And the rank of our I'm sorry, it's not k, it's m, because k is kernel, right? So the rank of the matrix is dimension minus kernel, which is m. It means that those vector fields are linearly independent. The first observation, we have already shown this formula that they do commute, right? So basically now we apply the Frobenius Ii theorem, and we do apply it in a sense we have discussed in the beginning. That is, we pick functions f which satisfy the following formula, right? Now, if we look and we see that the following holds, how? right? Why this formula holds. Okay, let's go back. L star is actually a transposed matrix. So it will be 0 here, 0 here, 0 here, and there will be vector fields in the rows of this matrix. And then you take this function d and you apply to this matrix, right? Multiply, and you'll see that you have m rows, and if the ith rows is equals to 1, this is exactly here, it stands for dy. So basically, this is just the same thing, just being rewritten, right, in terms of psi. So in terms of f, if you psi, you just open it. Or if you just write psi for in this formula, you get exactly this. So we get this formula, pretty nice formula, and we should keep in mind that we can take new coordinates x, new coordinates y, right? And we see that those x coordinates, they exact the f, those are the functions that are linearly independent, and those y coordinates are the integrals of this distribution, because we see if we take the differential of y and apply it to the function, to the vector field psi, then we get 0, because, well, because we have a formula where there is no, there's nothing here. If we apply the differential, it means that we need to multiply it by a row, which has zeros in the beginning and 1 somewhere here, and if you multiply it, you get 0. So basically, we get this condition, right? It's a simple condition. And we have this collection of functions, see? So we have k integrals and we have k first function. But m, as we recall, right? M, in our case, I'm sorry, I should not be k here, it should be m. It's a mistake, it's a typo. Okay, so we have m, we have two m functions, right? And it should be not n minus 2k, it should be n minus 2m. So we have a smaller, and we have, because see, we have here k is big, and we have small m, and we have m functions, and k minus m functions more we need. And that is where the second part of the discussion in the beginning kicks in, right? We've already discussed if we have some integrals, we can find some more integrals, right? Which will be linearly independent. And that's what we do. We just add some more integrals, which we call g, and we call z, and we get the following formula. Exactly. See, because of this condition, if we apply integrals, then we get 0, and we see that if we, because we have a complete collection of the coordinate functions, and we apply to it, we get the following formula, which looks very nice. Which again, these are typo. It should be inversed. K and m should be inversed. Okay, so this is the first step. What we basically did, we took an operator with this extra condition, yes, and we brought it to constant form. Now, the next step is to do the induction, right?
I'm sorry, I have a stupid question. Why m cannot be smaller than k? I don't understand. I'm sorry.
Because see here, k is kernel, right? Is the dimension of kernel. So if you assume that the k is smaller than m, right? You get the matrix with a long matrix M, right?
Yeah.
You understand it, right?
Yeah.
Okay, but the rank of this long matrix is it should be k, right? It's not the end of the explanation, but you understand it, right? You have a long matrix. You have smaller side and longer side. Smaller side is K, and longer side is M. So the rank of this matrix is at most K, right?
Yes.
Yes. So if you have a long matrix, then you can find a vector which multiplied by this matrix gives you zero, right? This is a simple linear algebra.
Okay. Okay. Thank you.
Yes. So it means that you did not pick all the kernel vector fields, right? Okay. Doesn't make any sense, or I just confused you more? Nadezhda?
What? I thank you.
Okay. I while explaining this, I came up with a second explanation, because if you have operator which is squared is 0, then it has Jordan blocks of dimension 2, right? And it has Jordan blocks of dimension 1. The dimension of kernel, right, is a dimension of Jordan blocks of dimension 1 plus the number of Jordan blocks of dimension 2. The dimension of the image is a dimension of is the number of Jordan blocks of dimension 2, right? So M is the dimension of the image. So it should be smaller. Okay. So it's a linear algebra. See how linear algebra interacts with us. So so this is the mistake here. So it should be other way around. Okay. But now we're ready to do the trick, to do the induction, right? So what happens here? First, we assume that the height is s plus 1, and we have a coordinates, and we have those, again, the first coordinates are the coordinates that basis vector field, they do span the kernel. So we get the following matrix. We have L2, and we have M, and we have some zeros here. Now let us calculate the Nijenhuis distortion. So we calculate the Nijenhuis distortion straight ahead. The calculations are similar, right? We use one of the partial x from the 0 column, and we see the following formula. We see it goes like this, because this is 0, right? And this is 0, and the fourth term is absent because those are basis vector fields. Then we get that the only term that survives is this. We expand it, right? And we differentiate it in x, see? And we see that this part, it vanishes because it is expressed in terms of partial x, right? Partial x beta, and it lies in the kernel of L. See, we have a kernel, so it vanishes, and we have only one thing left. We see what is it? We take an operator and we apply it to the following vector field, right? And look at this again. This is again an important thing about rank. So if we look at this column, we'll see that we have the rank of this matrix, because we took all the kernel here. The rank of this matrix, it is exactly the M, right? So it's M. You have M columns and columns along. And we have a linear, here we have a linear system. We have an operator L, and we apply this column, which does not have first K coordinates. We apply to this matrix, and we have a following linear algebra problem. We have a matrix, high matrix, not long, as we did before, and we apply a vector, and we need to get 0, right? It's so-called overdetermined linear system. And as the rank of this system is maximal, then the overdetermined system has only one solution. It is 0, right? Simple thing is, you keep in mind that the simplest example when it's not overdetermined, but of this matrix is a square matrix, right? If it has maximal rank, it is non-degenerate, and then if you multiply it by any vector to get a 0, you need to for this vector to be 0. This is basically the same only for high matrices, right? For those like in the height with long columns. It is absolutely the same. So we have a linear condition, linear operator condition. It vanishes, it should be 0. Okay. So this is 0, and we get that those L2 coefficients, right? They vanish all simultaneously, and it means that these L2, this operator, it does not depend on X. Okay. Awesome. We got ourselves an operator, and it is a quotient operator, right? We have a correctly defined quotient. Now we do just take the quotient space, right? We take local coordinates. We take a foliation, which is the integral foliation of the distribution of kernels. We take the quotient space. This is space of leaves. We have a natural projection of our operator on this nature of this space of leaves. Then we see that after we do this projection, right? After we do this projection, because it was a factor by kernel, we get that the height of the operator decreases. This is again simple linear algebra, right? Just go back because linear algebra might be sometimes confusing. We'll see that if we'll just do this factorization, we'll see that this row, it shortens a little bit, right? Because we already factored by kernel, right? And if it shortens the length of this row of this flag, the length of this flag, this is exactly the height of the operator. So if it shortens by 1, we get the operator is height smaller. It has the height has decreased. So if we have a smaller height, we can apply induction, right? And so we, without loss of generalization, we get that the operator is constant in these coordinates in y. So we assume that we've already did a coordinate change. It's only a coordinate change in y, because this is the meaning of the quotient space. And after we did a coordinate change in y, we got ourselves a constant operator. To understand it, to be more specific, we assume that the operator is in Jordan form, Jordan normal form. Each j is a Jordan form of dimension R1, right? Those are, some of them might coincide, those R's, they might coincide or might not coincide. It does not matter. But still we have a Jordan operator. So basically what we got is we got ourselves the following, this formula, right? We got ourselves the following formula. And after applying the induction, we got ourselves 0, 0, and here we have constants, which are Jordan blocks. It means that we have ones and zeros here, and we have some matrix here. So what we need to do is we need to make this part constant also, right? But what we actually already solved this problem, like similar one, not exactly like this, but we've already did this. So we first brought the operator to this form, and then we said, well, those vector fields, they do commute, right? And if they do commute, let's do the thing we already discussed in the beginning. The idea of the proof is the same. So the only difference and the complication we have here, right? We have one but important complication. We do not have zeros. We have ones and zeros. So some terms, some entries of these operators, they are zeros. There are a few of them, right? But there are some. So what we need to do is we take a multi-index, right, notation. So what we do is we split our m coordinates into the following subsets, right? We take upper coordinate and we just do two-step enumeration. First number, it defines the number of the block, and the second number defines the number of coordinate in the block, right? And these are the same coordinates. And notation we use, like every multi-index notation, is just, again, the coordinates have upper indices, and the differential, they have lower indices. So this is like this. So we have upper indices, and this is how we renamed our coordinate system after the coordinate change. So now we need to carefully take a look at this coordinate system. What do we have? First of all, again, if we do the transposition, if we take L star, we get this matrix. It goes here. It becomes long matrix. It's high matrix. It becomes long. and this becomes 0, and we see that this L star operator, it acts on differentials of coordinates y, very rather simple. By applying the J star, actually it acts. You see, right? So it says that it increasing the second number. It means that it stays in the same group, but the second number increasing till you get to the last number, and after you apply it, you get 0. This is exactly how Jordan block works, right? It just in case of vector fields, it increases your number, and it decreases actually your number in case of vector fields, and it increases your number if you take J star. So it's simply like this. Then, in terms of vector fields, we have a more complicated formulas because we take those y's, right? And we get this formula, and we get this formula. Here is we have a multi-notation, same as here, right? It means that we applied, we took the column which corresponds to the jth block and to the ith column in jth block. Here it is. We see that it's also rather simple, that Jordan block, it increases you, and you have this matrix M, it comes from this, it's upper notation, you have on the upper side. So in these coordinates, we just see we have this condition hold, and we see we have this condition hold. They're actually similar, quite similar. Now, if we look at this, right, and we apply again the coordinates, we see that the following formula holds, right? This L applied to the Y, because you have some constant here. After you commute it with a coordinate vector field, you get something like this, and you have a derivative of this in Y. So it lies in kernel, because it's just expressed in, it lies in span of this coordinate vector field, and lies in kernel. And this means if both of them, if those lie in kernel, then if we write L here, we get 0. So the entire, again, the entire Nijenhuis distortion, it looks like this, right? It looks like this, and 0. So we again get the collection of commuting vector fields. Now they have two notation, because we have Y have two notation, and we have again commuting vector fields. Now what we do, now we're almost exactly in the previous situation. We have a collection of commuting vector fields. Now we need to choose some of these, we need to choose a coordinate system for these vector fields. We do it in 4 steps. The step 1, we pick a coordinate functions for these vector fields, like for the vector fields with this number. It means that in each block we take first vector field, right? The first vector field implies that it has no constant part, right? It's just like this. And we take functions which for the coinciding numbers give 0, and for all others they do give, for coinciding numbers they give 1, and for others they give 0. See, and if we again do the transposition, because of these formulas, we get this relation for this function, right? Okay. Now this is first. We have new functions. New is the number of blocks, and new is the number of functions here. Okay. Now, I'm sorry. Now we take more functions, just those y's, right? And for them, we see that if we apply y, because we have 0, we do not only have zeros, but we have 1s in those Jordan blocks. Then applying this psi, we get this the following formula. That means that we add to the collection of f more functions, but we take them to be y's, because those are, see, these would be 1s, and if we transpose and apply differential of y, right, from this formula, you see that it still works, right? So it means that we picked the collections of f, and it is the complete collection of f, right? Those are, they satisfy this condition and this condition. They're linearly independent because of the, we discussed in the beginning. So we have a complete collection of L, because here we have for each block we have almost like the number of the functions in each block is smaller by 1. And here we have those ones, and we have all together. We have exactly m functions, right? We have exactly m functions. That means that the number of the vector fields, right? The number of the vector field psi is m, and we have exactly m functions. Those are the f functions we started with the beginning, and they're linearly independent because we have already this discussed. Okay, now step 3. We need to get the integrals, right? But it turns out that some of our functions, they're already integrals, some of our coordinates, right? Especially those coordinates, the ones in each block, there is the last coordinate, and it is integral for our vector fields, it turns out. So this is an expression, but you can, instead of this, you can imagine again that you transpose the matrix and you get just a 0 column. It means this is an integral, right? So we get, using this, we get new functions, right? New. And those are new integrals, and we take them to be y's. So what we did, we took all the y's functions, right? We split them into groups. One went into the f collection, and one went into the integral collection. And in the end, we are still do not have enough functions, right? And the rest of the functions we need, we have already m functions, and we have new functions integrals. Thus, for us to get the complete collection of functions, to get a coordinate system, we need a k minus new functions, right? And those are integrals of the distribution. That is why we take those new functions we have here, and we add enough integrals to get the complete list of integrals, which will be functionally independent. That's it. So the difference between first and the induction start and our induction is that in the beginning we only had actually step 1 and step 4, but here we had to go through step 2 and step 3, just carefully collecting functions. See, we almost had all the only what we need. We have had a lot of functions to complete the coordinate system. What we actually needed, we needed those functions, see, because we didn't know them, and we have those extra integrals because we did not know them, and that's it. Now we have a complete. We have a complete collection of functions. There are enough of them. They're differentially independent, and we get all the formulas for them together in this formula. See, I gathered all the information from the previous steps, and we see that this holds, and we see that HIs are exactly the one functions we need. Those functions are f, a, l. For l equals to 1, and we get those all together functions. So our matrix now consists of zeros and ones in these new coordinates. That completes the proof. So again, the proof goes like this. We start with a height equals 2. There we use we find a distribution, a good distribution. We take the coordinate systems associated with this distribution, and we already finished. And in induction step, we do find first a quotient operator, then we apply the induction step, and then we just carefully pick the functions to get the coordinate system for the new for the operator in this new coordinate system to be constant. That's the idea. So that completes the proof. So the corollaries then really nice. The first one is that if you have a Jordan block of maximal size that always can be brought to constant form, many people in different contexts have proven this theorem, and there are different proofs. But here we get it from the following fact. You see, the kernel of the operator in some power is just image of the power n minus the power, right? Because that's how you construct the Jordan block. Taking the next power is just increasing the kernel by 1 and decreasing the dimension by 1. So it goes like this. So basically, we see that those coincide, and because the images are integrable, we have the kernels that are integrable, and this is a great example of how algebra interacts with our differential geometry. And because images are integrable, we get kernels integrable, and we apply Thompson's theorem. Another example, very similar, is you have several Jordan blocks of the same size, right? Of the size M, you have several Jordan blocks. Then you get the same result. It means that the kernel is the image is the same, right? Not all the dimensions, they do allow such operators to exist, of course. But in our case, we get that this everything's okay. And those powers, they coincide. Those distributions, they do coincide. And again, because the image is integrable, the kernel is also integrable. Finally, let us recall that the GL regular operators, the operators we will deal later, but they're very important. It means that their powers are linearly independent. It's one of the definition, and the other definition which we need here is that for each eigenvalue there is only one Jordan block, right? You have eigenvalue and single Jordan block for this eigenvalue. If you have a constant, if you have a GL regular operator with real eigenvalues, then applying first splitting theorem and then applying the corollary for the Jordan block, you get that this operator can be brought to constant form. So if GL regular operator has real eigenvalues and its eigenvalues are constant, which is equivalent to the fact that the coefficients of characteristic polynomial are constant, then it is constant in some coordinates, which is a good example. Now, in the end, we will try and see what happens when there is no integrability of kernels. We start, as you remember, our proof, it started with the L squared equals to 0, and this is the case we're going to study. We'll see that even in this case, we already have an amazing variety of geometries, like the problem of if you ask, are there any normal forms for the operator which is Nijenhuis and satisfies this condition? The answer will be no, and there are a wild variety of geometries involved. So, okay, we start with the following theorem. It's not a normal form, you need to understand. So you can treat it as a normal form, but it's not unique, right? It's just a good form, a local structure. It means that, well, we say that in this case, we can take K. K in our case is a dimension of image, like it used to be the dimension of kernel in the proof, and now it's dimension of image. And if K is a dimension of image, it is smaller than the dimension of kernel, smaller than a half. We've already discussed this. So you will get this good part, which is constant, and you get this part, which has 0, but this submatrix of dimension K times M minus K, and it depends only on y's, but it's not constant in general. How do we prove this theorem? Well, the proof goes exactly like the first part of our part of proof of Thompson theorem, but we'll see the difference. Look, the distribution is integrable, so we take an adopted coordinate system and we get the following matrix. But you see the difference here, it's crucial that n it's what I tried to explain to Nadezhda earlier, right? So in this case, we see that the matrix is long. It has k rows and m columns, but m is larger than k. So we have a lot of columns, and the rank of this matrix, it's k, right? Because the image has dimension k. So, and this is important. And now, and those vector fields, they still, if we do perform the calculations and define the vector field psi same as before, using partial y's, then we see that those vector fields, they still do commute, right? And as they do commute, we can take the coordinate system as before. We take functions, k functions. Without loss of generality, we assume that the first k columns are linearly independent. If they are linearly dependent, we just switch the coordinates to make first k columns to be linearly independent. So we do that, and then we take those commuting vector fields and consider this shorter version of distribution, right? Smaller distribution xi. And what we do is we take functions f the same way as we did before, and we see that y's are integrals for these functions, right? For the k functions, and we take those y's as integrals, right? So we have a new collection of functions. We changed x's actually, and we changed x's and left y's to be the same, right? So after we do that, we get the following formula, right? It's a bidirect computation. It's rather simple, nothing complicated here. But important thing is m depends on both coordinates, right? X and y, both collection of coordinates. So what we do is we again do the calculation. See, we take, we know that in our case xi already partial x's. So we do the calculation of these two vector fields. They're supposed to be commuting. We get this, and we get that m in this form does not depend on x. So we have m depending on y, and we got the normal form. But how many how many are there such normal forms, right? Maybe we need to ask this question. Okay, so let us just change the coordinates back to the following we had here, but only without depending on x. We can do that, right? Because this is this formula here. It's basically ny, where this matrix does not depend on x. So we take this formula. This formula is nice because, first of all, for arbitrary matrix n, right, this is the Nijenhuis operator. For arbitrary function, we get the following formula. We apply the differential and we get the following formula, because what you do is you transpose it, because L star is transposed, and then you apply D and you get the following formula, and you see that if you want this operator to be zero, it means that those functions must be the integrals, right, of the corresponding vector fields xi we already discussed. Then we see that because the rank of this matrix is k, same thing as before. There we only use vector fields, and here we use differentials, but those linear algebra does not see the difference. But for high matrix, it means of the rank k, it means that those coordinates must vanish, right? Because it means that those derivatives must vanish. We see that the only coordinates that preserve this normal form are the following coordinate changes, like this. We see that it's a simple exercise to show that if this matrix depends on x, it's just a simple integration, right? You just, instead of g, you take f, those that supposed to give you ones for those commuting vector fields, for the first commuting vector fields, right? And you see that they're supposed to depend on x linearly, because their differential, their partial derivative should not depend on x, which means they depend linearly. So we basically get the following coordinate changes. Under this coordinate change, right, the n is transformed like this. It's multiplied from one side by h minus 1 and from the other side by g. We see, if we take a close look at this formula, we see that the rows of matrix n, they're transformed as a differentials. And this H matrix on the left side, it corresponds to the changing of the basis. So basically the rows of n are differential forms, not necessarily closed, just one differential one forms. And we can, what we can do, we can replace those forms, the collection of forms, with forms which are obtained from these by multiplying by some functions and by taking the linear combination. So basically, we deal with the differential, with some sort of ideal of differential forms. The zeros of these forms, right? If you have a collection of the forms, for each you can have a distribution, it's a zero. For the collection of the forms, the distributions intersecting and give you a distribution of smaller dimension. In this case, we get an interesting distribution, which is a dimension of m minus k, because we have k rows, they are linearly independent, and that means that the kernel of the collective kernel has a dimension m minus k. This distribution is on quotient space, actually. It lives on quotient space. And we denote it dn. We get the following proposition, that actually two forms of the operator of this form, they're equivalent if and only if the distributions are equivalent. See? Recall that in the beginning we noted that for any matrix n, this is the Nijenhuis operator. Thus, in the simplest case, when we deal with the L squared equals 0, the question of normal forms of these operators is equivalent to the question, right, of the classifying of the distributions of dimension m minus k on m-dimensional space. Basically, on classification of arbitrary distribution, right, without singularities, the rank of distribution stays the same in the neighborhood, but the question, this question, it is wild, right? We know that you cannot classify distributions, it is impossible. So we see, but the number of geometries we have here is huge. It means that you have different distributions, right? You have different operators for each distribution. You can construct operators, so it's a complicated problem. But we have a small we have a small trick up our sleeve, right? We see that these distributions, they might be integrable, for example, in case of I don't know, if for example the distribution has a dimension 1, right? It might be integrable. So in this case, it turns out that for even though the problem of classification distribution of the distribution is wild on itself, right? In some cases, we can find a good normal forms, and those are the forms of in small dimensions. Look, in dimension 2, every Nijenhuis operator is Jordan block of maximal size. So in dimension 2, every nilpotent operator of the constant rank, right? Of course, it can be brought to constant form. In dimension 3, if we have L squared not 0, then we have a Jordan block of maximal size, and it can be brought to constant form. But if we have L squared equals to 0, then we have a following set of numbers. We have k equals to 1. This is the image, right? And m is the number of is the dimension of kernel, which is 2, right? So in our construction, we get a one-dimensional distribution on two-dimensional space. One-dimensional distribution is always integrable. That is why taking enough coordinates, we can make this distribution that coordinate distribution, right? So this is the trick. And we see that we have completed an interesting result. In dimension 2, every nilpotent operator can be brought to constant form. In dimension 3, every nilpotent operator can be brought to constant form. That is why, going back to example we have mentioned by Kobayashi, we see that dimension 4 there is no coincidence. There is just no nilpotent operators that are not constant in smaller dimensions. So attacking the dimensions y by 1, you can probably, for smaller dimension, you can get the list of the at least you can get the list of examples. So in the end, I give you exercises as usual. The first two are actually exercises in linear algebra, just for you to get acquainted with the Nijenhuis operators. With the nilpotent operators, you need to calculate the Jordan normal forms using the dimensions of kernel and dimensions of images of those flags we had. And the following is assume that L has two-dimensional blocks and one-dimensional block, right? And prove that in this case, for arbitrary dimension, the operator can be brought to the following forms. These zeros, they're high matrices, which has dimension k in one direction and 1 in other dimension. This means that this is just 0 in the square. So it just has one long 0 column here and one long 0 row here, and the rest of the operator is constant. So that's it for today. Any questions?
Previously, you have a theorem stating that which says on the quotient manifold, some kind of L will become Nijenhuis, right?
Nijenhuis.
Can I see that? Nijenhuis, yes. What is that
Okay.
one? I was curious, is it also like if and only if? Or is there, yeah, this one. So
Yes,
this
exactly.
means you, so if, what is the condition? You said that L is already Nijenhuis, right? Nijenhuis.
Yes, L is Nijenhuis, and distribution
So
is
it's still Nijenhuis on the quotient manifold, right?
no. You have three independent conditions. One condition is the operator is Nijenhuis, right?
Mm-hmm.
Second is distribution is L invariant, right?
Invariant under L.
And under L, yes, of course.
Okay.
The third condition is that the quotient operator is correctly defined. This is the independent condition of Nijenhuis, right?
So that becomes a new Nijenhuis operator on M over F, right?
Yes, if those three because this condition
if
has
those
nothing.
three, fine, okay.
Yes, this condition it's a differentially geometric because this is linear condition. It's a linear algebra. This is differentially geometric, and this is differentially geometric. And this condition actually has nothing to do with an Nijenhuis torsion. It lives on its own, right? This is what we discussed. Here in this calculation, if you see, I've already used this condition when I say that L2 depends only on Y. See, I use this condition extensively to get this formula. Okay.
I see. Thank you. Thank you.
Welcome. Any other questions? Okay, then. Thank you very much. See you next time.
Thank you.